Here we are with our last video of section 3.4. This one is just going to hit some highlights of these last few pages of your notes. So if you look at page 26, this here is just reminding you, what the log graph looks like. And we talked about this before, so I'm not going to spend a bunch of time on it. But remember, whatever the base is, b, log base b of x, all of the graphs of these look pretty much the same. You do have a point at 1, 0, because the log of 1 is always 0 no matter what the base is. And then you have the point over here, b comma 1, if b is your base, because log base b of b is always 1. So that's your basic graph. Down below that, you have a place to put the domain range and so on. And we've done that before, so I think we're just going to skip that for now. If you go over to the next page, 27, it says, describe how to transform the graph of the natural log into the graph of the given function. Again, I don't want to spend a whole lot of time on this, but basically what they're talking about is this. We just saw that if you're going to graph log base 5 of x, it's going to have the point 1, 0, and then it's going to have the point 5, 1. And that looks like this. Now, what they're talking about is transforming the natural log graph to look like that. If you take this and convert it using the change of base formula to a natural log, you get the natural log of x over the natural log of 5, which you can also think of it as 1 over natural log 5 times the natural log of x. And I put this 1 over natural log 5 into my calculator, and I got 0.621. So really, that means that this log base 5 of x is equivalent to 0.621 times the natural log of x. In other words, a vertical shrink by a factor of 0.621. So we know that e to the x, or rather natural log of x, is a graph that goes through 1, 0, and then it also goes through the point E1, looking something like this. And if you have log base 5 of x, you just take this graph and shrink it by a factor of 0.621, and then you would get these points. So, like this point right here would be e comma 0.621. And so that's what this is referring to. Just something to be aware of. Again, you probably wouldn't use this a whole lot because we know how to graph log base 5 of x. Just graph 1, 0 and 5, 1, and you've got it. On this next one here, the base is 1/2. Now, the same rules apply where you will have the point 1, 0 on the graph, but you will also have the point 1/2, comma 1. Notice that 1/2, 1 would be up here. When you connect those, your graph is going to be different than the previous one. It's going to be a decreasing graph. And it's sort of interesting to look at that compared to the natural log graph, just like we did on the previous one. Think of this as natural log x over natural log of 1/2, or in other words, 1 over the natural log of 1/2 times the natural log of x. I put 1 over the natural log of 1/2 into my calculator and got negative 1.44. Which makes sense because, your natural log graph looks like this. And this negative means it's been flipped over the x-axis, and then it's been stretched by a factor of 1.44. So you can see where this decreasing graph now comes from. But all of your log graphs, no matter what the base, if the base is greater than 1, it's going to be increasing like this. But when the base is less than 1, that means that what has happened is it's been flipped over the x-axis. So you still have this point b comma 1. It's just that b is less than 1 there. So kind of an interesting comparison between those two. Now, the last thing I want to talk about here is on page 28, where we have the scatter plot that we need to make here. This data represents the price and quantity demand for a personal computer. We want to draw a scatter plot, and then it's going to ask us to fit a logarithmic function to the data. I know that earlier in the chapter, we did exponential regression and we did logistic regression. This logarithmic regression is different from either one of those. Remember, exponential looked like this, where it had exponential growth or exponential decay. So these were exponential graphs. Then you had logistic graphs, and those were those S curves. So we did some of those. Now this is going to be a logarithmic graph, which is going to have a shape like the logarithmic graph we just looked at. It's going to be either an increasing one like this or a decreasing one like this. So these are the logarithmic type shapes. These are the exponential shape. And then this was the logistic shape. So here they're asking us to do logarithmic. So let's get our calculators out and let me clear this out. Go into your stat edit and put that data into your calculator. If you want to pause the video while you do that, you can. Once you have the data in there, then you're going to go to Stat, Calc, and let's choose the right one here. Down here at the very bottom of my screen is LN reg. That is natural log regression. And that's what you're going to choose when you're doing logarithmic regression. Again, remember earlier we did exponential regressions and we did logistic. Don't confuse logistic with logarithmic. So you want to pick this number 9 right here, the natural log regression. So make sure you have your two lists chosen. Store the regression equation into Y1. Remember, those of you without the new operating system will just have to do natural log regression and then vars, y-vars, function, y1. Okay, so here's my equation. It's y equals a plus b times natural log of x. A is 569.75 and b is negative 53.9. If you go into your y equals, that should be now into your y equals. Make sure your plot is turned on. I've got my plot 1 turned on. List 1 and list 2 is where my data is located. And then you can zoom stat, that's number 9, and you can see here there's your data and that logarithmic graph fits there. And that's like the logarithmic regression graph that you would get. It's actually a natural log graph. So when it asks fit a logarithmic function to the data, you're going to put this equation that you got right here. So let me just copy that over. Oh, nope, that was wrong. Try that again. Copy that. Okay. Okay, so here's my equation, really humongous. There we go. Okay, and then it says use the function above to find the number of personal computers that would be demanded if the price was $1,500. Now, remember back over here, the price was the X value, so that makes it pretty easy. All we have to do now is put in 1,500 for the X value. So I'm going to take this 1,500 and I'm going to plug it in right here into the equation for X. So I'm going to be taking that 569.75 minus 53.91 times the natural log of 1,500. And that should give me the result that I'm looking for. So let's do that here. And so I get about 175 computers would be demanded in that case. And if we look back at our data here, whoops, just kind of make sure that makes sense. You know, if you've got $1,500, you're right in here between 14 and 1,600, and 175 is right there in between these two values. So that seems reasonable. So answer 175 computers. All right, there's not a problem like this necessarily in your homework, but I just wanted to make sure that you knew how to do those logarithmic regressions. You may see one on a review, on a quiz. Make sure you know how to do that. All right, that concludes section 3.4. And we just have one more section in the chapter, 3.5. Now for that section, I do not like the notes that I gave you there. So those pages from section 5, you can just rip those out and throw them away. I'm going to have different ones to give you for section 5. All right, talk to you later.